All right. So hello and namaste everyone. Welcome to lecture 10. So before we advance, do you have any quick questions with regards to what we have done so far? Please raise your hand. All right. So I don't see any raised hands. So maybe we can do a quick recap of what we did last time and we can continue from there. Right. So if you remember last time, okay, we sort of looked at this concept called as a matrix representation of a boundary operator. Right. So this is in a sense not a new concept to you all because you have all done a course on linear algebra and you must all be familiar that let's say if you have two vector spaces V and V prime and let's say V is some n dimensional space and let's say this is some n dimensional space, right? So let's say this is n dimensional and let's say this is m dimensional, right? So which means that one can find a basis so that both for V and V prime, okay, so that we can represent the coordinates of the vectors in V and V prime using vectors in Rn and Rm respectively, right? So one can do that, and if we have some operator T over here, then one can find a matrix representation for this, right? So this is something that in one way or the other you must have studied in linear algebra, and that's the reason a course on linear algebra mainly focuses on studying this properties of matrices and so on and so forth. Okay, this is the main reason. The main reason is that any linear operator, okay, one can sort of study its properties by looking at the matrix, looking at its matrix representation. All right. So in the same way, we realize that, oh, Daba P is a linear operator or it's a vector space homomorphism between the vector spaces CP and CP minus 1. Right. So this is something we have been discussing all throughout this course. So then we said, OK, if this is a linear operator, then one can look at its matrix representation as well. Right. So however, the difference between this figure that you must have studied in your previous courses and this figure is that we work with vector spaces over Z2, right? So that's the difference, which means that, if you try to find the, find a basis and identify the coordinates of the chains in CP, then the vectors, the corresponding vector of coordinates, okay, will lie in Z2 to the power FP, where recall FP is the number of P dimensional faces, right? And similarly, CP minus 1, okay, the coordinates of this will be vectors in Z2 raised to Fp minus 1, where Fp minus 1 is the number of P minus 1 dimensional faces in the given simplicial complex, right? So if Daba P is the operator, then this notation over here denotes its matrix representation, and you can see that there is S and S prime over here. Okay, so these are emphasizing the basis that we use for CP and CP minus 1, and S and S prime over here represent the standard basis, right? So standard basis means for CP we look at so let's say we let B be the basis for CP, right? So in this case B will be sigma 1, sigma 2, blah blah blah, all the way up till sigma sub FP, right? So these are your chains with support 1, right? And this chain has support sigma 1, this chain has support sigma 2 only, and so on, right? So this forms a basis for CP, right? And similarly we can look at the basis for this CP minus 1. So this will be tau 1 blah 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 all the way up till tau FP minus 1, right? So I've used a different symbol over here, okay, which is tau only for convenience. Okay, so this are the labels for the different P minus 1 chains with support 1, right? So you put them all together and that set will form a basis for CP minus 1, right? Okay, so this is so I should actually use S and S prime so that there is no confusion. So this will be S, right? So this will be S and this will be S prime. All right. Okay, so I hope you all are aware that the matrix representation depends on the choice of the basis, right? So that's why we sort of explicitly highlight what the basis is for the domain space and what is the basis for the codomain space, right? And from this we can figure out what would be the dimension of this matrix, right? So so this dimension comes from the basis that we have, number of elements in the basis that we have for the codomain space and the domain space, right? So the number of elements here is fp minus 1, the number of elements in this basis, and the number of elements in this basis, that is the basis for the domain, is fp, and accordingly one can see that you have fp over here. So this matrix would have a dimension fp minus 1 cross fp, and all the elements of this will come from the underlying field, which is Z2 here, right? So this will be a fp minus 1 cross fp matrix, and the elements of this matrix would either be 0 or 1, right? And we have to figure out which coordinate will be 0 and which coordinate will be 1. In order to do that, we make use of the following relation, right? So this relation is basically coming from this figure that we have over here. Okay, so this figure tells us that this diagram is commutative, which means that if you start from here and land up here in this direction, or if you start from the same place and end at the same place in a different direction, whatever is the result that you will obtain, that should be one and the same, right? So you can see that this over here represents what happens if you move along this direction, right? So you start from some C. If you come down over here, this is the coordinates of this chain in this basis S. Then you take this vector in Z2 FP multiplied with this matrix, and you end up with what you have on the left hand side, right? So this is this, right? So this is what you have. Now on the other hand, you could have also moved in this direction, in which case you start with C, you apply this boundary operator, right? So this is an element in CP minus 1, and you can figure out what its coordinates are. So the coordinates of this will be daba P of C, and you look at its coordinates in S prime, right? So you can see that this is the right hand side of this. So this diagram commutes means that in whichever way you proceed, you end up with the same answer, right? And that's what is written over here. So this is true for any chain C in CP, right? And since we want to figure out what this matrix is, let's say we are interested in knowing what the the jth column of this matrix is. In order to figure that, we can take this matrix and multiply it with ej, right? So we don't know how to do this multiplication. However, we are aware of this relation. So what we do is we try to find out that chain whose coordinates are ej, right? And it is not difficult to see that the sigma j p chain. Okay, so this is the p chain with support on sigma j only, right? So if you look at the coordinates of this with respect to the standard basis, then this indeed is ej, right? So this indeed is ej. So now we have an expression that looks very much like this. So this must equal this. So from this we can say that this must be daba p of sigma j. So there is a typo here. This should be s prime here, right? So you look at daba p of sigma j. And you look at the coordinates of this with respect to the S prime basis. So I hope you agree that daba p of sigma j will be a p minus 1 chain, right? And one can ask, what are the coordinates of this with respect to the basis S prime that we have chosen, right? So from this relation, it follows that the ijth entry of this matrix will be 1, right? If tau I, so this is a p minus 1 phase. So let's say you order the p minus 1 phases in some way, and let's say tau I is the ith p minus 1 phase in the ordering that you have chosen. So this is a p minus 1 phase, right? And this is some p phase. So if tau I is a subset of sigma j, or if tau I is one of the phases or boundary phases of sigma j, in that case we will say that the ijth element is 1. Right, so let's look at a quick example and see how to compute the boundary matrices associated with a given simplicial complex. So let's say this is the simplicial complex. It has 4 vertices, 5 edges, and 1 triangle. So let's see how to compute daba 2. Right, so before we compute daba 2, we have to first make sure we understand what its dimension are. Right, so accordingly, what we see is that C2 has dimension 1. Right, so this has so maybe I'll write it this way. So the first thing is we notice that dimension of C2 is 1. So why is the dimension of C2 1? Because there is only one triangle, and that will form the basis for this C2 vector space, and that's why dimension of C2 is 1. On the other hand, dimension of C1, okay, since there are 5 edges, this will be 5. Right, so accordingly, daba 2, okay, will be will have a matrix representation. So ideally I should say daba 2 S prime, right? So this is what I should write. S prime is a 1, sorry, it should be 5 cross 1 matrix. Okay, so this is how you should write it. Okay, but we will be sloppy, and instead of using this cumbersome notation, square bracket, have a basis below, have the other basis above. This is sort of ideally how one should write it. However, this is sort of too many notations and it's going to unnecessarily bother us. So what I'll do is I will sort of simply represent the matrix representation of DABA2 by DABA2 itself. Right, so of course this is not correct. DABA2 is an operator. However, I will sort of leave it to the context and to your judgment to figure out, when I write DABA2, does it represent the operator or does it represent the matrix representation? Okay, so mathematicians like being sloppy because they don't want to be hindered and be obscured by these notations. However, they always make sure that whenever they are being sloppy, there is an unambiguous way of deciphering what is written. Okay, so I sort of say this sentence time and again, so to emphasize that some of these notations may not be appropriate. Okay, so this is a sloppy way of writing. Nevertheless, based on the context, you should be able to unambiguously figure out what I am saying. Okay, so this DABA2 actually is a matrix representation of the operator DABA2, and as we saw, this is a 5 cross 1 matrix, right? And what you do is you order these edges in some way, right? So there are 5 edges, so I have decided to order them in this way: 1 2 1 3 1 4 2 3 3 4. So this is the ordering that we decided, right? And 1 2 3 is one of the triangles, so there is only one element, so we don't have to really worry about the ordering. So what we do is you write all the two-dimensional faces as the columns and all the one-dimensional faces as the rows, and then you put a 1 wherever if this one face is a boundary face of this 2 face, right? So indeed 1 2 is a boundary face of 1 2 3, that's why you have a 1 here. Similarly, you have a 1 here. However, 1 4 is not a boundary face of 1 2 3, that's why we have a 0, right? So again, I would like to emphasize, right, memorizing how to put these ones and zeros, okay, is more like maybe a high school level. In fact, I don't even encourage it at high schools. Okay, I want you to understand why we get these ones and zeros. Okay, then the answer to that comes from this relationship over here. Okay, so please just don't memorize some rule saying, okay, here is the reason why it should be 1 and so on, right? I hope so if you memorize, you will have the issue that if I change the underlying field and so on and so forth, okay, the memory rule will not work. Is that okay? However, if you understand what exactly is the reason why we have these ones and zeros here, okay, it will be very natural, if you change the underlying field and so on and so forth. All right, sounds very good. Okay, so this is how the DABA2 matrix is. Now we have to look at the matrix corresponding to this DABA1 operator. Again, the first thing we have to do is we have to understand what are the the dimension. What is the dimension of this DABA1 matrix, right? So it goes from C1 to C0. The dimension of C0 is the number of vertices that is present here. So its dimension is 4, whereas the dimension of C1 is 5, right? So hence DABA1 will be Z2 to the power 4 cross 5. Right, so it will be a 4 cross 5 matrix whose elements are whose elements come from Z2, right? So what I do is I choose some ordering of the vertices, right? So I just call them 1 2 3 4. Notice that this ordering and this ordering is the same, right? So this is very, very important that these orderings be the same. So whatever ordering you want, you choose. But once you decide that ordering, you should not change it. Okay, so notice that the ordering that we assign to the edges here and the ordering that we assign over here, okay, they are one and the same. And accordingly, we can now construct these different columns. So you sort of put a 1 if this vertex is a boundary face of this edge and so on and so forth. So in this way, you can come up with this DABA1 operator, right? So I hope you agree that DABA2 must be identically 0. Sorry, not DABA2. It should be DABA to the power 2 should be identically 0, right? So this must be DABA1. What should I say? Composed with this. Okay, this should be identically 0, right? This is what this expression over here means. So if you have done things correctly, okay, it should follow that if you take DABA1, DABA2, it should end up being 0. Is this okay? So this is something you should be able to verify, and that you can use as a sanity check to make sure that you have defined the matrices correctly. All right, so let me pause here. This was just a recap of what we did in the last class. Nevertheless, let me have a quick pause over here and allow some of you, those who have questions, to put them uh, put them to me. Do you have any questions? All right. So surprisingly, I don't see any raised hands. So any case, so let's advance. Right. So recall, why are we doing all this? Right. So the end goal is somehow to use some computational algorithms to figure out what these Betti numbers should be. Right. So that's our goal. So you can see that we already have matrices. So now we can use these matrices, do operations. Right. So matrices are very natural to modifications using a computational algorithm. You can take a matrix, do something, blah blah blah. You can add rows, you can subtract rows, you can do matrix vector multiplication. All those things are quite natural in a algorithm that you can run on a computer. So I hope you are all very excited. Oh, we can now do all this shape related business on a computer, right? So I hope if some of you have been following the whole story, right? So we started by asking, how do I look at the shape of a simplicial complex, right? So then we said, oh, this simplicial complex is just a collection of sets. Then we said the shape of this should correspond to the geometric realization of this simplicial complex, right? So when we say we are looking at the shape of this simplicial complex, we are actually talking about the shape of its geometric realization. Right. So when we sort of think about it, okay, I mean, just imagine when we started out with this geometric realization and things like that, it was a bit of I mean, it was a bit strange to think how would we come up with an algorithm to do all this, right? So but now you can see that we are at the end of the day working with linear algebra. We have some matrices and we have to use these matrices to figure out what the shape is, right? So at this point, if you haven't yet managed to appreciate it, I sort of would like to emphasize that this is the beauty of mathematics, right? So we started off with a goal of trying to figure out what the shape of a simplicial complex is. At the end of the day, the math behind us gives us some matrices. Okay, and now as a from an engineering side, we can look at these matrices. We can say, oh, now we have to compute its rank, column rank, null space rank, and so on and so forth, right? This doesn't seem very hard because this is something that as an computer engineer you should all be familiar with, and then you can figure out, oh, this is a very inefficient way of computing this rank, maybe we can speed up things, and so on and so forth, right? But the underlying story comes from mathematics. Okay, so I hope you are able to see the connection between how math actually helps and how computer engineering sorts of helps us speed up these algorithms and so on and so forth. All right. Okay, so so far so good. So now what we are going to do is we are going to use these matrices and then try to figure out what these different Betti numbers are, right? So one of you, I was hoping that one of you would ask me, why have I written only these two, the matrices corresponding only to these two operators? What about the operators daba 0, daba -1, daba 3, and so on and so forth, right? So because of the example that we are considering, all these operators, okay, will be empty matrices, right? So this is because either one of the dimension will be 0 or both the dimensions of the vector space, which is either the domain or the codomain of these operators, okay, they will all be 0. Okay, so that's the reason. So I would like to emphasize that currently we are working with this usual homology setup. That's why the dimension of daba 0 or the daba 0 is also an empty matrix. Is this okay? But later on, like maybe in a page or so, we will look at the reduced homology setup. There indeed, for the same example, this daba 0 will not be an empty matrix. Okay, so I thought I will emphasize this. All right. So now we are interested in computing the Betti numbers using the matrix representation of the boundary operators. Okay, so what we are doing is that, look, we know how to compute the Betti numbers by looking at the homology groups, figuring out what the basis is, and thereafter looking at what the dimension of that homology group is. Here what we are doing is, notice that in order to construct these these matrices, nowhere did we compute this homology groups, right? So notice that these boundary operators, only looked at what these domain and codomain vector spaces are, in particular what this CP and CP minus 1 is, right? So that's all we needed to know, and computing these matrices is very easy, right? So you just have to look at which p minus 1 face is a boundary of which p face, and accordingly you can figure out where you will have these ones and zeros and so on and so forth, right? So computing these matrices never required you to look at what the kernel is, what the homology groups is, and so on. So I hope you can see that these boundary operators are indeed quite easy to write down. So now using these boundary operators, we are going to compute the Betti numbers, right? So we will first recall the formula of these Betti numbers. So recall that Betti k is the dimension of hk, right? And what is hk? Hk is zk quotient bk, and there was a theorem that we discussed which told us that dimension of hk, since it's a quotient of two vector spaces, this must be dimension of zk minus dimension of bk, right? So this is something we figured out. So that's what I have written over here. Now what is dimension of zk, right? So dimension of zk is the kernel of the Daba k operator. So that's what I have written over here. And what is bk? Well, it's the image of Daba k plus 1 operator. So dimension of bk is precisely the dimension of image of Daba k plus 1, right? Now from our linear algebra class, we would know that the dimension of the kernel of a linear operator is precisely the rank of its null space, right? So kernel of Daba k, recall, is kernel of Daba k is basically all chain in Ck such that Daba k of C is 0, right? So this is the collection of chains which is mapped to 0, and we are interested in knowing the rank of or the dimension of kernel of Daba k. Well, this is precisely the kernel of the null space of Daba k, right? And similarly, if you want to look at the dimension of the image of Daba k plus 1, well, this is precisely the column rank of this matrix Daba k plus 1. So again, when I write Daba k here, this is the matrix, right? Because the null space of a matrix and column rank and all those things are defined in the context of matrices. However, when I write Daba k here and Daba k plus 1 here, I actually mean them as operators. All right. So now let's figure out the null space rank and the column space rank of these different operators for the above example, right? So recall what the above example is. So the above example has these four vertices, and then we have this triangle over here. All right. Okay, so what's the procedure? Okay, so I'm going to dictate the procedure for in this particular example, right? And I would hope that you understand the basics and you are able to extrapolate it to different examples as well, right? So let's look at this Daba 2 operator, right? So Daba 2, as we saw before, is this 5 cross 1 matrix, and its entries are as given over here, right? And the question now is, so this is a linear algebra question. The question is, this is a matrix that has been given to you, and I'm asking you what's the rank of its column space and what's the rank of its null space. Okay, so that is what is the question. Right now in linear algebra, you must have studied this some set of rules which would have guided you to figure out the rank of the null space and the column rank of a given matrix. Right, and if you recall, one of the ways of looking at this was to reduce such a given matrix into the row reduced echelon form, right? And in order to get this into the row reduced echelon form, right, any given matrix, you must have studied the usage of these following three row operations, right? So if you remember, we were allowed to exchange rows, we were allowed to multiply a row with a scalar C which is not equal to 0, and as a third step or a third operation, we were also allowed to take a scalar multiple of a row and add it to another row, right? So these three row operations we were allowed, right? However, in our case, right, since we are working with matrices over Z2, right? So Z2, recall, only has two elements. So Z2 only has two elements, 0 and 1. In particular, the number of non-zero elements in Z2 is only 1, right? So this is something we observe. So it follows that, let's look at this second operation, right? So in the second operation, we were allowed to multiply a row with a scalar C which is not equal to 0. But the only non-zero element that we have is 1. And if you multiply a row with a non-zero scalar, we would end up with the same row. So this operation is in some sense redundant, right? I hope you agree. in the when we were dealing with row operations over matrices defined over a real or complex field, right? So there we could multiply it with some non-trivial scalar, right? Like non-trivial scalar meaning like 2, maybe pi, maybe 100, maybe -2, and so on, right? So all those things were allowed because both z and both the set of complex numbers and the set of real numbers, okay, have infinitely many non-trivial scalars, right? However, in Z2, right, we are only having one non-trivial scalar element, right? So this operation from that perspective is redundant. So this operation is kind of we don't have to specify. So this operation is really doing nothing, right? So the only operation then we are left with is 1 and 3. So let's look at the third operation. So the third operation says we can take a scalar multiple of a row and add it to other row, right? However, again, the only non-trivial scalar is 1. So the third operation basically says take one row, add it to the other row, right? So in Z2, we are only left with these two operations, right? So either you are allowed to exchange rows or you can take one row and add it to the other. Is this okay? So these are the only two operations that you are allowed, right? And one can now see that since we started off with this matrix over here, right, you can now do a series of row operations and get it down to this matrix, right? So you can take the first row, add it to the second row, so you would end up with 0 here. You take the first row and add it to the fourth row over here, and you would end up with 0, right? So I hope you agree that this would be the row reduced echelon form corresponding to this matrix over here, right? And from this matrix we have to now decipher what the column rank is and what the rank of the null space is, right? So the number of columns here is 1, right? That's the first thing we observe. The number of columns is 1, right? And the other thing we observe is that this is a column that has a pivot entry, right? So this one over here is a pivot entry, and because of this reason, the column rank, right? So the column rank turns out to be 1. Okay, so column rank of DABA 2 is 1, right? Now from the rank nullity theorem, okay, so the rank nullity theorem says that the column rank plus the rank of the null space must equal the number of columns, right? So one can use that relation to figure out that from the rank nullity theorem. Okay, of course you can figure out it in some other way as well, right? So from the rank nullity theorem, the rank of null space of DABA 2, okay, so this is 0. Is this okay? So this is what we find out. Okay, so let me pause here. If you have any questions, please ask. Please let me know if you have any questions. All right, so I don't see any raised hand, so maybe we can advance. Okay, so this was a very simple exercise. We sort of looked at this DABA 2 and figured out what the column space of DABA 2 and its rank of its null space should be. Okay, so this is what is the conclusion. Okay, so this 1 and 0 is something you have to remember. Now let's see if we can do something similar with this DABA 1 operator, right? So I will sort of go over a few steps, and then I will presume that all of you can proceed similarly. So here is the DABA 1 operator or the DABA 1 matrix, right? So so it has for example 1 1 over here because these two vertices are the boundary vertices of this edge. Similarly, there is 1 1 here because these two vertices are the boundary vertices of this edge, and so on, right? So we want to figure out what the rank of the column space and null space of this matrix is. That is our question, right? So again, we would like to do a series of row operations, get it down to the row reduced echelon form, right? And from there we can easily decipher what the dimensions of these desired spaces are, right? So as you remember, the only operations that we are allowed here is exchange of rows and adding one row to the other, right? So in order to get it into the row reduced echelon form, we notice that this is already 1, right? So we don't have to do any exchange operation. So we don't like this one, right? So we can try and reduce it, right? So to do that, what I do is I add R2 to R1, and whatever is the result, I write it in R2. Right, so this is how I get, and I am making use of the fact that 1 plus 1 is 0, and 1 plus 0 is 1, and 0 plus 1 is 1. So that's how I get this row. I leave these two rows untouched. Okay, so then I come to this second column. So the first column is, is of the way that I would like, because this is how a row reduced echelon form should look like. Okay, but then I move on to this second column. And then I noticed that this is not in the form that I would like in a row reduced echelon form. In particular, these are two elements that I don't like. So that's why I take this element, add it to this element, and take this element and add it to this. And in order to do that, I implement these two row operations. Right. So accordingly, I get this column over here. So you can see that I got the first column the way I want in a row reduced echelon form. Similarly, I have this second column the way I would like in a row reduced echelon form, and I can proceed accordingly. Okay, so I'm sure each one of you is competent enough to proceed in this direction, right? So you keep doing all this, and you eventually end up with this matrix over here, right? So let's make sure this is in row reduced echelon form, right? So you first look at the the non-zero entry over here, the non-zero entry over here, and the non-zero entry over here. You can see that the first non-zero entry in the first row appears before the first non-zero entry in the second row, and similarly the first non-zero entry in the second row appears before the first non-zero entry in the third row. Okay, and all zero rows are at the bottom, so that is something we can ensure. And furthermore, we can see that all entries in the pivot column other than the pivot entry. So these are the pivot entries. So other than them, all these entries are 0. Okay, so if you sort of go back to the definition of this row reduced echelon form, you will see that all these conditions are required, right? And this matrix indeed satisfies all those conditions, and we can say that this matrix is in the desired row reduced echelon form, right? And now we have to decipher what the column rank and the rank of the null space is. Right, so we sort of see that there are three pivot columns, right? And from this we can see that, so there is no pivot entry here and there is no pivot entry here, right? So consequently, one can see that the column rank of DABA1 is 3, right? And again, from the rank nullity theorem, one can see that the rank of the null space of DABA1 is 2. Is this okay? So this is what we can figure out, right? So this is what we have figured out. All right, so let me pause here for a second or two. If there are any quick questions on how I figured out the column rank and the rank of its null space and so on, or if you have any questions on the different operations that we did, please let me know. I'd be happy to explain. Okay. Yes, Ichit, go ahead. Do you have any question?
Yes, sir. I want to ask whether in this case, I mean, in all the cases also, that column rank will be always be equal to row rank, isn't it?
Column rank will always be equal to row rank. Yes. So is that your question,
So,
or you are making that as claiming, I mean, making that statement?
yeah, I'm making that statement.
Yes, that is
Uh,
indeed true. Yes.
so why do we say here column rank of DABA 1 instead of rank of DABA 1?
We can say that I'm just being explicit because we are interested in looking at uh, uh, um, the image of. So if you recall the definition of beta k, right? Beta k is the dimension of kernel of zk. Sorry, not kernel of zk. So it is kernel of daba k minus dimension of image of daba k plus 1. Is this okay? So this is what we require, and I am just emphasizing that we are looking at the column rank. You are right that we can just say it as the rank of this matrix. You are right. Hmm?
Okay, sir. Thank you.
Any other question? Any other question? All right. So I don't see any raised hand. So maybe we can now advance. Okay. So what we have done so far is the following. So let me just summarize. We were given this matrix, sorry, this simplicial complex. We looked at DABA2 and DABA1. Okay. We focused on only these two matrices because these were the only non-empty matrices. Okay. All other matrices, including DABA0, would have one of the dimensions as 0, because of which those corresponding matrices would be the empty matrices. Is that okay? I shouldn't even say the zero matrix. It is the empty matrix. Is this okay? And because of this reason, we only looked at DABA2 and DABA1. And now we sort of computed the column rank of both these operators as well as the rank of the null space corresponding to both these operators, right? And we did that by reducing both these operators to their row reduced echelon form, from where we can easily decipher what their column rank and rank of their null space should be. So we were able to decipher them, and now we have those numbers, right? So now we can look at what Betti 1 is, what in general what Betti k is, right? So let's begin by looking at what Betti 1 is, right? So Betti, maybe first we begin by looking at Betti 2. So let me see if I have already computed Betti 2. Okay, I have not computed Betti 2 here. So let's write down what Betti 2 is. So Betti 2 is dimension of kernel of DABA 2 minus dimension of image of DABA 3. Is this okay? So this is how Betti 2 is defined. Now we have not explicitly written down the matrix associated with DABA 3 because it's an empty matrix, right? So so in particular, we can go back to this DABA 3 operator, and we can see that this goes from C3 to C2, right? And C3 is a trivial vector space, so this will only get mapped to 0 here. Hence the dimension of the image of DABA 3 is going to be 0. So I'm just going to write 0 over here. So let me use a different color. So this is going to be 0, right? And what is image of kernel of DABA 2, right? So image of kernel of DABA 2 is something we already figured out, and we saw that this is actually 0, right? So the number of columns of in DABA 2 was 1, and it was having a pivot entry. So from that we concluded that the column rank of DABA 2 is 1. And from there we computed that the kernel of the rank of the kernel of DABA 2, or the rank of the null space of DABA 2, must be 0, and hence we managed to figure out that this is 0. Is this okay? So now let's look at what Betti 1 is. So Betti 1 is dimension of kernel of DABA 1 minus dimension of image of DABA 2, right? So this is the rank of null space of DABA 1 minus the column rank of DABA 2, right? So we now know that the rank of null space of DABA 1, right? So the rank of null space of DABA 1 is 2, right? So I can write 2 over here minus the column rank of DABA 2. So this is 1, and we end up with 1 over here. Is this okay? So we finally see that beta 1 is 1, and this is what we expected, because recall what the given simplicial complex was. So this was 1, 2, 3, 4, and this was the triangle that was filled, and this is the cycle that was hollow, and that's why one expected that beta 1 turned out to be 1, right? So now let's look at beta 0. So beta 0 is a dimension of kernel of DABA 0 minus dimension of image of DABA 0, right? So what is image of DABA 0? So image of DABA 0 is something we figured out. So this is 3 over here, and now we have to figure out what is the dimension of kernel of DABA 0. So now DABA 0 is an empty matrix, so we cannot use the things we discussed above in the context of DABA 0, but we sort of recall that C0 is mapped to C minus 1, and since we are working in the usual homology, this is the trivial vector space, so which means that every element in C0 is mapped to 0, right? So the kernel of DABA 0 is precisely dimension of C0, right? And we know that dimension of C0 is basically the number of vertices. So this is 4 minus 3 and this is 1, right? And we can see that beta 0 actually turns out to be 1 in the usual homology case. Is this okay? So let me pause here for a second or two if there are any questions with regards to how we computed beta 2, beta 1 and beta 0, right? And I hope you also agree that for any other Betti number, in particular, if I asked you what is Betti k for any k, I hope you agree that one can easily figure out that it must be 0, and that just follows from the fact that both these dimensions are 0. Is this okay? So let me pause here for a second or two. If you have any questions, this would be a good place to ask. Okay, I don't see any raised hand, so let's advance. Okay, so I hope you agree that all these calculations concern the usual homology setup. Okay, so one can also ask, okay, can we do these calculations in the reduced homology setup as well? Well, indeed we can do. There is nothing different actually happening conceptually. Conceptually, what is happening is that there are vector spaces, there are linear operators between these vector spaces, right? And we can look at the matrix representation for them. Now, the only thing that has changed in the reduced homology case is that C minus 1 in the usual homology case was just the trivial vector space. This time it is Z2. That is the only difference, right? And so now we just have to figure out, okay, what are the changes that are induced because of this new definition, right? So I hope you agree that daba k for k not in 0 minus 1, right? Recall that daba p or daba k goes from ck to ck minus 1, right? So c minus 1 being defined as Z2. So this is a new definition of Z2. So this is only going to affect daba 0 because C minus 1 will appear here, and daba minus 1 because C minus 1 will appear over here. Okay, so these are the only two operators which will be affected because of this change of C minus 1. And correspondingly, we only have to worry about, what is the matrix representation for daba 0 and daba minus 1. Okay, now for daba minus 1, okay, so this is not very difficult because daba minus 1, okay, goes from C minus 1 to C minus 2, and in the reduced homology case, C minus 2 is said to be the trivial vector space, right? So because of this reason, the matrix corresponding to daba minus 1 before as well in the usual homology case also was an empty matrix, and in the reduced homology case also it will be an empty matrix, right? And this is what is something you have to keep in mind, right? And now let us look at what beta minus 1 is, right? So beta minus 1 is a dimension of kernel of daba minus 1 minus dimension of image of daba 0, right? So this is a dimension of kernel daba minus 1. So let's try to see what is dimension of kernel of daba minus 1. So daba minus 1 is a map that goes from Z2 to the trivial vector space, which is 0, right? So every element in Z2 is mapped to 0. Hence the kernel of daba minus 1 is precisely C minus 1, right? And dimension of C minus 1 is precisely 1, right? So this part is something that we can figure out from the definition of kernel of daba minus 1, that this is 1, right? And now what we need to figure out is what is dimension of image of daba 0. Right, so let's try to figure out what is this image of daba, dimension of image of daba 0. Now in the usual homology case, daba 0 was this empty matrix, right? However, in the reduced homology case, this daba 0 actually will not be an empty matrix. So we will have to figure out what this matrix is. Again, we follow the same philosophy. Daba 0 is an operator between C0 to C minus 1. right? Now C0 has dimension F0, which is the number of vertices in C0. So if you want to look at the coordinate representation of the zero chains, we have to look at them in the space Z2 to the power F0, right? Whereas C minus 1, right? C minus 1 is only including 0 and 1, right? So this has only two elements and its dimension is 1, right? So I mean, in fact, you can think of C minus 1 as telling us the coordinates themselves, right? Like what I'm trying to say is, if you look at Rn, right, and if I ask you what are the coordinates of the vectors in Rn, and if you look at the standard basis, then you will say that every vector is its own coordinate representation, right? So in the same way, Z2 here, okay, you can think of that as the each element in Z2 as being the coordinate representation of itself, right? Because C minus 1 is the trivial, like it's Z2 itself, right? So one can write Z2 over here, and now one can ask, well, this is the linear operator over here, what's its matrix representation, right? So the matrix representation, first we figure out that the matrix will have dimension 1 cross F0, right? This would be the matrix, right? 1 cross F0. So this will be the matrix representation, I mean the dimension of the matrix representation of this Daba 0, Daba 0 operator, right? So this is something we notice. So let's look at our example, right? So in our example, you have these four vectors, these four vertices, right? And so then the matrix corresponding to this Daba 0 operator will be a 1 cross 4 matrix, right? So it has one row and 4 columns, and each column will correspond to these different vertices that we have, right? And I'm claiming that all these elements over here will be 1, right? So can one of you help me figure out why is the matrix representation of Daba 0 given by this matrix over here? Can one of you please help me figure out why is this all ones? Yes, Jacob, please go ahead.
When we take the image of 1.
Yes, what do you mean by 1?
The vertex 1, the 0 chain.
0 chain corresponding to 1. Is that what you're saying?
Yeah.
Okay, so what is this?
This consists of odd number of vertices. So when we do summation, it will be 1.
Okay, so this will be mapped to 1. Very good. So how does this tell us that the first column of this matrix should be 1? How does that tell us?
1's coordinate is 1 with respect to C2.
Very good. Okay, so what I'm saying is that this is what we have to actually do. So we sort of take this, let's say we want to figure out the first column of this matrix, right? So this we know is Daba 0 S prime, and as Jacob pointed out, if you look at the vertex 1 and if you sort of look at its representation with respect to the standard basis for C0, then this is what we will end up with, right? That this representation will indeed be E1, right? And this now equals Daba 0 of 1, and we have to find its representation with respect to S prime, right? Now Daba 0 of 1, because 1 is a 0 chain with odd number of like the support being odd, like the cardinality of the support being odd, it follows that Daba 0 of 1 is 1. And now we have to find its coordinate, the coordinates of 1 with respect to S prime, right? However, C minus 1 is Z2, and the basis for Z2 is precisely 1, right? So from this we can see that this coordinate of 1 with respect to S prime is precisely 1, right? And this sort of tells us why the first coordinate over here should be 1, and similarly one can argue why these coordinates should be 1 themselves. Is this okay? So this is how you can see that the matrix representation of Daba 0 in the reduced homology case actually turns out to be this, right? And now one can again talk about what is the column rank of this matrix and what is the rank of the null space associated with this, right? One can immediately see that this is in row reduced echelon form, right? And because it's in row reduced echelon form, and since there is only one pivot column, right, the column rank of Daba 0 is actually 1, right, whereas the rank of its null space will be from the rank nullity theorem 4 minus 1, which is 3, right. So from this one can first finish off what beta minus 1 is. So beta minus 1 was 1 minus the column rank of Daba 0, right. So we have now figured out that the column rank of Daba 0 is 1, hence beta minus 1 turns out to be 0. On the other hand, beta 0 is what should I say, this is the dimension of kernel of Daba 0 minus dimension of kernel of sorry, not kernel, this should be image of Daba 1. So this should be image of Daba 1, right. So now we haven't touched Daba 1 in any way. So whatever was our calculation before, we just have to use it. So now what has changed is that kernel of Daba 0, earlier the dimension of kernel of Daba 0, when I say earlier, I mean in the usual homology case it was 4, now it is only 3, and the dimension of image of Daba 1 was 3 before, it is 3 now as well, right. So this turns out to be 0. Is this okay? So in the reduced homology case, you can see that beta 0 is actually 1 less than the Betti 0 in the usual homology case. Okay, so I sort of I have been asking you to think about why we work with the reduced homology case, why we work with what is the difference exactly, right. So first thing is, why does Betti 0 decrease, and what is the purpose of having this Betti 0 decrease by 1 in the reduced homology case, right. So I'll sort of give you one more lecture to think about. In the next lecture, maybe I'll give the reason why this Betti 0 in the reduced homology case is 1 less than the usual homology case, and in particular why this is useful, right. So in fact, I haven't even told you what Betti 0 actually counts in the usual homology case and in the reduced homology case, but by now you should have managed to figure out that in the usual homology case it counts the number of components in a given simplicial complex. So this is in the usual homology case, and in the reduced homology case beta 0 is precisely number of components minus 1, right. So like for example, if you are given let's say a simplicial complex like this, right, in the usual homology case, if you look at Betti 0, it would be 2, whereas in the reduced case, so this will be usual, and in the reduced case this would be 1, right. Whereas if you looked at let's say something like this, then in the usual case this will be 1, whereas in the reduced case this will be 0. Is this okay? So let me pause here for a second or two. If you have any questions, please feel free to ask them. I hope what I'm explaining is, not completely vague. I hope there are at least bits and pieces that most of you are understanding. Okay. If there are any questions, please feel free to ask them. Please don't hesitate. All right, so I don't see any raised hands, so maybe we can move on. Okay, so now we have sort of, so far we have discussed computing these Betti numbers and so on of a given simplicial complex, right? So now we sort of move on to this next algebraic tool, which is called as the Mayer-Vittoris sequence, right? So we will first try to figure out, first try to motivate what is the purpose of studying this Mayer-Vittoris sequence and how is it going to be of use to us, and thereafter we will see the details of this Mayer-Vittoris sequence. Okay, so this Mayer-Vittoris sequence is actually named after two Austrian mathematicians, okay, by their name Walther Mayer and Leopold Vittoris. right? So I was actually looking up their names on Wikipedia, and I noticed some surprising things. So these two actually work together. In fact, you can see that Mayer was born in the year 1887 and Vittoris was born in the year 1891, right? So you can see that they were born roughly around the same time, right? But Mayer sort of passed away in the year 1948 around the age of 61, whereas Vittoris passed away very recently. Of course, recently is relative, but in 2002 at at the age of 111, right? So when you sort of look at the time at which these two people passed away, you can see that there is a significant gap, but nevertheless, these two people work together, and this Mayer-Vittoris sequence is one of the most powerful tools in homology, right? And I also, while I was looking up the Wikipedia page, I also noticed something interesting. It appears that this Walter Mayer was actually Einstein's assistant. Okay, so and he was often referred to as Einstein's calculator or something like that. All right. Okay, so this was a short digression. So now let's try to see how is this Mayer-Vittoris sequence going to be of use to us. So of course, I haven't told you what this Mayer-Vittoris sequence is, but nevertheless, before studying anything, I often find it useful to understand what is this sequence going to be of how is this sequence going to be helpful to us, and then I sort of study the properties and the definition of this sequence, and then make sure that indeed this thing is helping us in the exact way that we had understood before, right? So let's first try to see what is this Mayer-Vittoris sequence and how is it going to help us. Well, it's an algebraic tool. Okay, that is the first thing. And this Mayer-Vittoris sequence is going to be useful to compute homology groups or homology spaces of complicated topological spaces, right? So of course, the Mayer-Vittoris sequence is going to be of use in generic setups, but in this whole course, we will be making use of this Mayer-Vittoris sequence in the context of simplicial complex, because that's our bread and butter in this course, right? So we will be focusing on these simplicial complexes, and this Mayer-Vittoris sequence is going to help us figure out the homology spaces associated with these complicated algebra simplicial complexes. Okay, so that's how this Mayer-Vittoris sequence is going to help us. And broadly speaking, how does it, enable us to compute the homology groups of these complicated simplicial complex? So let's say X is a given supposedly complicated simplicial complex. Okay, so again, what complicated means and so on, we will soon see. At this point, let's say it's a simplicial complex whose homology spaces we are unable to figure out. Okay, easily. Of course, with some effort it may be possible, but maybe it's not easy to figure out what the homology spaces what are the homology spaces that are associated with this given simplicial complex. So in that case, we will say X has a complicated structure, and the key idea in the Mayer-Vittoris sequence is to compute the homology of X by splitting X or decomposing X into simpler subcomplexes, right? So let's say the simpler subcomplexes are A and B, right? And we choose this A and B so that the homology of A and B is in some sense relatively easy to compute. Okay, so the idea is the following. We want to express X as A union B, right? So X is a given simplicial complex, A is another simplicial complex, B is another simplicial complex, and the property is that A is a subcomplex of X, B is a subcomplex of X, and A and B are chosen in such a way that their homology is easier to compute. And what we want to do, or what the Mayer-Vittoris sequence enables us to do, is to somehow relate the homology groups of X with the homology groups of A and the homology groups of B. That is the purpose. Okay, so I haven't yet told you what this Mayer-Vittoris sequence is, but nevertheless, without giving you the details, I have managed to tell you that it's a tool which will help you figure out what the homological groups or the homology spaces associated with X are in terms of the homology spaces of A and the homology spaces of B. Is this okay? Now, this is what this Mayer-Vittorius theorem tells us. Okay, so we will not be seeing the Mayer-Vittorius theorem today. We will see it in the next class. What is the exact statement, right? But nevertheless, let me give you an example of how this Mayer-Vittorius theorem could be used. Okay, so let's say we have been given some simplicial complex delta, right? So here is some simplicial complex delta, right? And so let's say somehow we manage to figure out what its homology spaces are, right? So let's say we somehow manage to figure out what its homology spaces are, and now let's say I modify this simplicial complex slightly, right? So let's say I add this triangle and I leave the other things untouched. Okay, so let me repeat. Jayant, do you have a question? Jayant, can you unmute yourself?
Yes, sir. So actually, I was like wondering what is homology spaces, like I forgot.
So you remember these HKs, right?
Yeah, yeah.
So these are the homology spaces. So you remember this is defined as ZK quotient BK, right? So these are the homology spaces. Is this clear?
Yeah, thanks.
Okay, so these are the homology spaces. So if you remember, the whole of this homology theory concerns itself with finding out what these HKs are for generic topological spaces. In this course, we are interested in finding out what these homology spaces are corresponding to simplicial complexes. Is this okay? And what this Mayer-Vittorius theorem will enable us to do is that, let's say we have been given this in some complicated abstract simplicial complex, and A and B are subcomplexes of this, which we choose in such a way that somehow computing the homology groups of A and B are easy. Homology groups or homology spaces of A and B are easy, right? And using the homology spaces associated with A and B, we want to figure out what the homology spaces of X are. That's the goal. Okay, so that's what this Mayer-Vittorius theorem will help us. And here is such an example. So here is a simplicial complex, right? It has a bunch of vertices and it has a bunch of edges, right? And so let's somehow presume that somehow we managed to figure out what the homology spaces associated with this simplicial complex are, right? So by that we mean, somehow HK for all K in Z. Right, so let's say you somehow manage to figure this out. Maybe you put in a lot of effort, you did your calculations using paper and pen and managed to finally figure out what these homology spaces are for different K, right? And let's say tomorrow I ask you, okay, you have managed to figure this out. Now can you go ahead and find out the homology spaces associated with this new simplicial complex, right? Now notice that the difference between this and this is that there is an additional triangle over here, right? Whereas the number of vertices, the edges, and so on and so forth, everything else is the same, right? However, you can see that there is an additional triangle for the example on the right. So now if I ask you, can you somehow find out for me what are the homology spaces associated with this? So now, if you are a person like me, you would say, oh God, I'm not going to do it. Okay, I spent so much time, figuring out the homology spaces associated with the simplicial complex on the left. Okay, you have just now changing one thing and you're asking me to do this process from scratch again, right? So this is really, very cumbersome and I'm not going to do it. If you are such a person, you would then find lot of use in this Mayer-Vittorius sequence. Right, so the Mayer-Vittorius sequence can be used in the following way. So let's say this is X, right? Now what we will think of the simplicial complex that is given to your left is A. So A, I hope you agree, is a subcomplex of X, right? So the first thing you notice is that A is a simplicial complex and every face in A is also a face in X, right? So because of that reason, A is a subcomplex of X. Now let me define B to be this simplicial complex, right? So this is all the three vertices, all the three edges, and this triangle. I hope you agree that, okay, X is actually equal to A union B, right? So it is very important that both A and B be simplicial complexes. So the reason why we require A and B to be simplicial complexes is that only for simplicial complexes can we define these homology spaces, right? If it was just a triangle, right, we cannot talk about its homology spaces. So what do I mean is that when we talk of B, we require that B include the three vertices, the three edges, as also this triangle. So we require all these spaces to be present in B. Okay, we don't want B to be just made up of 1, 2, 3. This is not what we want. This is what we want, because then we can talk about the homology spaces associated with B. Right. So how can we use the Mayer-Vittorius theorem to compute the the homology groups associated with X, right? So X is slightly different to this A that is there on the left, right? And then we sort of cook up this B so that X is A union B, right? Now you put in lot of efforts to figure out what the homology spaces are. What are the homology spaces that are associated with A? And now you put in some effort to figure out what are the homology spaces associated with B, and the Mayer-Vittorius theorem will enable you to take these homology spaces and these homology spaces, combine them, and figure out what the homology spaces of X are. Okay, so this is just an example. By that I mean, the way I decomposed A and B and so on and so forth. Okay, so this is just one way of looking at things. The idea works whenever X is some simplicial complex and A and B are subcomplexes of X, such that X is A union B, right? So whatever be A, whatever be B, as long as A union B is X, you can somehow find a relation between the homology spaces of A and B and the homology spaces of X, right? So this is the advantage of the Mayer-Vittorius theorem. Okay, so I have still not stated what it is and so on, but nevertheless I have stated what its usage would be. Okay, all right. So now let's see. So I gave you some idea that, look, you have this simplicial complex. This simplicial complex differs from the simplicial complex on the left just by the addition of a triangle. And then we can use this Mayer-Vittorius theorem to figure out the homology spaces of X in terms of the homology spaces of A and the homology spaces of B. This idea you should be able to immediately generalize and say that, oh, look, if someone gives me some, very weird looking simplicial complex, let's say something like this, right? So something like this, maybe there is some tetrahedron somewhere, right? So let's say there is some tetrahedron somewhere, and we are required to compute the homology of this entire simplicial complex delta, right? So it is going to be quite hard, but it you must have immediately seen that look, we can use this Mayer-Vittorius sequence in a sequential Mayer-Vittorius theorem in a sequential fashion. So what do I mean by that? So let's label these vertices. So let's say 1, 2, 3, 4, 5, 6, 7, 8, and maybe 9. Okay, I hope I have labeled all these vertices, right? So this is the simplicial complex. What I will do is I'll try to construct this simplicial complex in a sequential fashion. So what do I mean by that? I first start with only this one vertex, right? I hope you agree that, if I just gave you this simplicial complex and if I asked you to compute its homology spaces, this is very easy, right? I hope you agree, right? So this is very easy. In the same way, let's say I give you this, a single vertex, 2, only this, right? And if I asked you to compute the homology spaces of a single vertex, that is also something you can easily figure out. And now the Mayer-Vittorius theorem will allow you to figure out the homology spaces associated with the union of these two vertices, right? So you manage to figure out what the homology spaces of this vertex is. You manage to figure out what the homology spaces of this vertex is, and now you can look at the homology spaces associated with their union. And similarly, you can add these different vertices one by one, and you can sequentially update the homology spaces of the resulting simplicial complex, right? So you can do it in this fashion. Let's say you sort of add these vertices in this way. So at this stage, you will know the homology spaces associated with the union of these 9 vertices, right? And then you can slowly add this thing over here, right? Let's say you add this edge, and now you can ask what's the homology space of this simplicial complex, right? And then you can add let's say this 2, 3 edge, and 3, 4, maybe 4, 5, and so on and so forth, right? So you can sequentially build your simplicial complex, and in parallel you can update your homology space description, okay, using this Mayer-Vittor's theorem. So let me pause here. If you sort of have any questions with regards to what I'm stating over here, please let me know. I would like to emphasize that there is a popular algorithm by Edelsbrunner and Delfinado. Okay, if I'm not wrong, this came in the year 1992, and actually they formalized this idea, and you will soon see, hopefully in the next lecture or maybe the one after that. Okay, we will actually see how we can use the Mayer-Vittor's theorem to come up with an algorithm. Okay, a very simple algorithm to compute in an incremental fashion the Betti numbers of a simplicial complex. Is this okay? So we are just basically trying to figure out different ways and more efficient ways of finding out the Betti numbers. You have already studied one way where you can first look at the boundary operators and look at their what should I say, their column rank and rank of the null space and use them to compute the Betti numbers. Okay, so that is well and good. However, you can see that, if you sort of only rely on that algorithm, you will face the issue that if I change the simplicial complex slightly, then you will have to redo the calculations from scratch. Right, so that's why the Mayer-Vittor's theorem is going to help you when you sort of only modify this simplicial complex in a minimal fashion. Okay, so let me pause here for a couple of seconds. If you have any questions, please let me know. Yes, Jacob, please go ahead.
While the decomposition happens, we must make sure that everything is a simplicial complex.
Very good. Okay, so that is important. So whenever we decompose, A and B should be a simplicial complex. In particular, when we look at this incremental thing, right, we have to make sure that at any stage, what we have is a simplicial complex. The reason for this is that if you don't have a simplicial complex, you cannot talk about its homology. Is this okay? So that's why we have to ensure that at any given stage, what we have is a simplicial complex. Like you cannot take this triangle, take these vertices and suddenly decide, okay, I will add this triangle over here, right? That is this 187, right? Without adding its edges first. So that, so let's look at this collection of, sets where you have these different vertices. You don't have these edges. So maybe I'll put some cross over here. So these edges are not present in your collection, but you have this triangle, right? So such a setup is not useful because we cannot talk about its homology because it's not a simplicial complex. Does that answer your question, Jacob?
Yes, and also while taking the partition, is it a partition like?
It's not a partition, right? So I have not said that A and B have to be a partition, right? In this example that I gave you, I hope you agree that A that is over here and B that is over here, they share 3 vertices in common. Do you agree? They share 3 vertices and they also share these 3 edges. Do you agree?
Oh, yes.
So they are not a partition. So how to choose A and B? At this point, I am not specifying, I am being a bit vague. But all I say is that you have to choose A and B so that A and B's homology is relatively easier to compute and you can use them to compute the homology of X. Is that okay? So whenever, how do you choose A and B? The answer to that is somehow A and B's union is X. That's the first requirement. And the second requirement is that in some sense, computing the homology of A and computing the homology of B is easier. Okay, so that's at this point the vague rule. I have not specified to you how to look at how to figure out what A and B should be. Okay, but here is an example where you spend a lot of time computing the homology of this, and the homology of B is also easy, right? Because intuitively you can see that there are no holes, right? So you can figure out what the homology of this should be very easily. Right, and the Mayer-Vittor's theorem will enable you to use the computations of this simplicial complex and this simplicial complex to figure out what the homology spaces are with this relatively complicated simplicial complex. All right, okay, so in the last 15 minutes or so, I won't have time to describe what the Mayer-Vittor's theorem is. However, the Mayer-Vittor's theorem requires understanding of something called as the Mayer-Vittor's sequence. And in today's class, we will sort of understand these concepts over here. In fact, I don't think we'll be able to look at this, the whole of this, but maybe we will only be able to look at a bit of this. nevertheless, let's try to proceed. Okay, so what is a Mayer-Vittorich sequence? Right, so let's say we have been given a collection of vector spaces A0, A1 all the way up till AM, right? And we have been given a bunch of homomorphisms between these vector spaces. So recall, when I say homomorphism, you have to immediately see that, oh, I am talking of these maps between vector spaces, and hence this homomorphism must be a vector space homomorphism, right? So this is what we have been given, right? So we start with AM, AM minus 1 all the way up till A0, and between these successive vector spaces we have a homomorphism, right? So this eta m will go from AM to AM minus 1, this eta m minus 1 will go from AM minus 1 to AM minus 2, and finally, I mean, this continues all the way, and finally from A1 to A0, between them you have this eta 1. So you can see that you have a sequence of vector spaces, and you have these linear operators or vector space homomorphisms between them. So this is at this point a sequence. We will say such a sequence is a Mayer-Vittorich sequence. Such a sequence is a Mayer-Vittorich sequence if the following relationship holds, right? What is the relationship? You look at successive vector space homomorphisms, and you require that the kernel of the this homomorphism be the equal to the image of this homomorphism. Okay, so that's what I have written over here, right? So you have AM, you have AM minus 1, and you have AM minus 2, right? So here you have eta m, here you have eta m minus 1, right? So kernel of eta m minus 1, right? Kernel of eta n minus 1, I hope you agree, is a subset of am minus 1. Similarly, image of eta m, this will also be a subset of am minus 1. Is this okay? And we will say that such a sequence is said to be what should I say? This is said to be a Mayer-Vittorich sequence if these two sets, right? If these two sets are one and the same. Okay, so that is what I have written over here. So whenever the kernel of eta m minus 1 equals the image of eta m, and this should be true for all m, right? So this should be true for all m. That is, it should be true for this what happens between the kernel here and the image here, and so on, right? So this should be true for all m. Maybe I should be a bit more clear. So this should be true for all m between 1 and m. Is this okay? So this should be true for every eta 1 to so maybe I shouldn't talk of image of eta 1. So maybe it should be true from 2 to n. Is that correct? So this is correct. Yeah, so this seems okay. Okay, so we want that this relationship be true for every m in 2 to m. That is, it should be true over here. It should be true all the way up till a1. Is this okay? So that is what we require. So this is what is a Mayer-Vittorich sequence. Whenever you have a sequence of vector spaces and vector space homomorphisms defined between these vector spaces, such a sequence is said to be a Mayer-Vittorich sequence if such a relationship actually holds true, right? Now, there is a special Mayer-Vittorich sequence which will play a very crucial role in this Mayer-Vittorich theorem, right? So what is special about this? So in this sequence, let's say m is 4, right? And the first and the last vector spaces are trivial, right? So let's look at such a sequence, right? So what I have done is I have taken this sequence. I have written it exactly in the same way as it was before. The only changes I have made is now m is said to be 4. So we have A0, A1, A2, A3, A4. And in addition, I require that both A0 and A4 be trivial vector spaces. So that's why I've set it to be 0, right? So here 0 means that it's a trivial vector space, right? So it actually means that this is a vector space only having one element, and that element we have to view as the additive identity, right? So whenever m is 4 and the end vector spaces are trivial, then the Mayer-Vittorich sequence that we end up with, we will refer to such a Mayer-Vittorich sequence as a short exact sequence, right? So the short, I hope, is clear. right? So clear meaning that this is short in the sense that there are only 5 vector spaces, and the first and the last one are trivial, and the exact thing over here means that the kernel and the image of successive maps, okay, satisfy this relationship over here. Is this okay? Now let's try to figure out what is the significance of this short exact sequence. Okay, so maybe I'll pause here for a second or two. If you have any questions with regards to this definition, please let me know. Yes, Jacob, go ahead.
Why is it called short?
It's short because in some sense, if I understand correctly, it has only 5 vector spaces, right? So recall that in general, you can define this sequence for any number of vector spaces, right? And this one that is short, it has only 5. That is one reason. So one can ask, why can we not look at 4, 3, and so on? Okay, so to be honest, I don't have a very good answer, but if you ask me to guess, then my guess would be that anything shorter is not really useful from the perspective of this homology. Okay, so that's my guess. I emphasize that it's only a guess, but this is called short because it is shorter than this generic definition that we have over here. Is this okay? All right. So this is a short exact sequence. Now let's see what are the properties of such a short exact sequence. So since it's an exact sequence, at each of these places, the image of the the first homomorphism should equal the kernel of the subsequent homomorphism, right? So let's look at what happens over here. So my first claim is that image of eta 4 is 0, right? Image of eta 4 is 0. So this is to be interpreted as so image of image of eta 4. Okay, this is a subset of A3. Now A3 is a vector space, right? So it will have an additive identity. So image of eta 4 only consists of this additive identity, right? That's what this statement over here means. Image of eta 4 is actually a set, okay, and it only includes an additive identity, right? So instead of saying that it only has this additive identity, I will simply say that it is I'll simply write it as 0. So this has to be interpreted that this is a vector space which is trivial in nature, right? So can one of you tell me why the image of eta 4 when I write something like this is 0? Can one of you please tell me why that is the case? Why is this true? Yes, Pankaj, please go ahead.
Because of homomorphism property.
Very good. Okay, so eta 4 is a homomorphism, right? So that automatically implies that the 0 on the left should be mapped to the 0 in A4, right? So that's why the image of eta 4 must only include this element 0 that we have over here, right? So now because of this exactness property, we require that image of eta 4 must equal the kernel of eta 3. Okay, so this must be true. Right now, since image of eta 4 is 0, it immediately follows that kernel of eta 3 must be 0, right? And one can then conclude from this fact that kernel of eta 3 is 0, it follows that eta 3 must be an injective map, right? So whenever you have a short exact sequence, the claim is that this eta 3 map which goes from A3 to A2, this must be a injective map, right? So what does injective mean? It means that it is 1 to 1, right? So let's look at a quick proof of why eta 3 must be an injective map or a 1 to 1 map. So we will use proof by contradiction. Suppose this eta 3 is not a 1 to 1 map, right? So eta 3 goes from A3 and let's say this is A3 and let's say there are a bunch of elements, and not 1 to 1 means that I hope you agree that there are two different elements which get mapped to the same element over here, right? So what we will assume is that let's say this is V, this is V prime. So V and V prime are different, right? However, the output of V and V prime under eta 3, they are one and the same, right? So that is the meaning of the statement that eta 3 is not 1 to 1, right? So this statement over here implies that eta 3 of V minus eta 3 of V prime must be 0, right? So the 0 over here, okay, this is an element of A2, right? Because eta 3 takes an element in A3 and maps it to A2, right? So this must be an element in A2. Now, because eta 3 is linear, okay, I can say eta 3 of V minus V prime must be 0, right? So this statement should tell us that eta 3 of V minus V prime is 0, right? So this automatically tells us that V minus V prime must be an element of kernel of eta 3, right? And V and V prime have been chosen to be different. So this implies that V minus V prime is not 0. So this automatically implies that there is a non-trivial element in the kernel of eta 3 which contradicts the given condition that kernel of eta 3 is trivial, right? So I hope you agree that kernel of eta 3 being trivial automatically implies that eta 3 must be a injective or a 1-to-1 map, right? And now let's look at the other property that is implied by a short exact sequence. So we have A3, we have A2, we have A1, and we have 0 over here. So let's look at what happens to the story on this side, right? So now because eta 1 takes A1 to 0, we require this automatically implies that kernel of eta 1 is A1, right? Kernel of eta 1 is A1 because every element in A1 gets mapped to 0 under this map. That's what this that's what this symbol over here means, that every element in A1 is mapped to 0. Hence kernel of eta 1 is A1, right? Now since kernel of eta 1 is A1 and this is an exact sequence, we have that image of eta 2 must equal kernel of eta 1 and which is equal to A1, right? So in particular this tells us that image of eta 2 must be A1. Okay, so this implies that eta 2 must be a surjective map. Okay, so this statement over here implies that eta 2 must be a surjective map. Okay, so maybe this is a good place to stop. Let me stop recording, and if you have any questions, I'd be happy to take them.